Hello there, Mr. Sutton here, bringing you the Algebra 2 6-2 lesson on the natural base e. In this one, we're going to be simplifying expressions that have this natural base. We're also going to graph exponential functions that have that as the base. And, just for fun, we're going to find interest with some continuous compounding. We're going to start our journey by talking about the number e. Yes, that's right. E is a number, kind of like pi and some other things, like I, that we've encountered in math before. So e specifically is called the natural base. Now the base is the number that you're raising to some power. So, for example, in the expression 2 to the x, 2 is the base. E is just another number that you can raise to a power. Now, what's so special about e? Well, we found through practice that e tends to show up in a lot of real-life natural situations. It's just one of those weird numbers that appears out in nature, and we're not really sure why. But here's what e equals numerically, and this is going to be a little bit weird. So e is, and this is called the limit as x approaches infinity. We'll talk about that in a sec, of 1 plus 1 over x to the x power. So this, what is this even? But we'll break it down a bit. This 1 plus 1 over x to the x power, this is kind of like that compounding interest formula, except you can change what the compounding period is. And this lim sort of stuff here, this is a fancy way of saying in calculus, we're basically saying what happens to the value of this thing as x gets really, 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 really big. So what does happen to the value of this thing? Let's actually go on Desmos and check this out. So here's Desmos, and let me just make a function for that e expression. So we'll do parentheses 1 plus fraction 1 over x, and let's raise that to the x power. And now let me start plugging some things in. So if I plug in, let's just plug in 10. That's not very big, and we get about 2.59. If we do 100, now we're about 2.7, so it hasn't really grown a whole lot. If we do 1,000, it grows a little bit more, but not much. 10,000, still not really growing. 100,000, million, right? We could keep going, but we're seeing that this is kind of flattening out at around 2.718. I mean, it keeps going, but it's not growing a whole lot. So we can round this off to about 2.718. And there's really no reason for you to round it off on the calculator, because if you actually go on Desmos and type in e, you'll see that it gives you the value of e anyway. That's built in and predefined. So now that we've defined e, let's use it a little bit. And by the way, e is irrational, in case you were wondering. It is like pi in that it just keeps going forever and ever with no pattern. At least none that they found. So let's do a few problems where we just kind of work with e and simplify it. Now e is just a number. There's no real special properties of e. It's not like I, where if you square it you actually get -1. E is just kind of like pi in the way that we use it. You can treat it like a variable, even though it's a constant, but it behaves a lot like a variable in these expressions. So pause the video and just use what you know about basic exponent rules to see how many of these you can simplify. All right, let's go through these one at a time. So we have e to the third times e to the sixth. I'm just going to add the exponents. So e to the ninth, nothing super fancy there. This next one we're dividing now, so that means we have to subtract the exponents. 16 over 4 is 4, and we've got e to the 5 minus 4, so that's e to the 1, or just e, so 4e. Next, we've got all this being raised to the second power, so we have to square each thing individually. When I square the 3, I get a 9. When I square e to the -4x, I'm multiplying the exponents, so that's going to be e to the -8x. And then finally, if we're taking the square root of these things, we square root each individually, which really means raising it to the 1/2 power. So square root of 4 is just 2. And actually this one I almost forgot to mention, we can turn that exponent into a positive by using the reciprocal. Okay, going back to this one, square root of 4 is 2. And we're dividing by 2 when we square root something, with the exponent anyway. So we've got e to the 1x to go with that. For the next couple problems, we're going to do a little bit of graphing. We want to first determine whether this function is exponential growth or decay, and then graph it. So pause the video and see if you can graph this first one. In fact, see if you can graph the next two of these. So the next one is this one right here, y equals e to the negative 0.5x. So there's nothing really different from what we did in the last lesson with graphing. So pause the video and give both of those a shot. All right, let's go through each of these. So this first one, we have a b value of e. This is where you kind of have to know what e is numerically, and it's helpful to know that it's around 2.7. That means that we are greater than 1. So since b is greater than 1, that means that we've got some growth going on. And let's just do a table from -2 to +2. Plug all those into 3e to the x and see what it comes out to. So for this, I am going to use Desmos. So we've got 3e and then exponent, and let's do -2 first. That's about -0.41. And then if we do -1, that's about 1.10. And 3 times e to the 0 is just 3 times 1, so that's just going to be 3. This is going to be 3 times e to the 1, but again, e is a decimal, so let's plug that into Desmos, so 8.15. And then finally, we plug in 2, and that's about 22.17. So I'm going to make a scale that's appropriate to go from basically 0 to 22 and some change. So we've got -2, 0.41, that's very close to the x-axis, and then -1 and then 1 roughly. 0, 3 is about there. 1, 8 is roughly here, and then 2, 22 is somewhere between 20 and 24. So again, we're just approximating this, and then we have that nice exponential shape with that asymptote going on as we go to the left here because we've got a growth function. Now let's take a look at this next one that you already tried on your own. If you didn't, then feel free to come back and do it. So since we have e to the negative 0.5, that's our b value there. What's the value of that? Well, if you're not really sure, I mean, there's no harm in plugging that into Desmos just to find out. So e exponent -0.5 comes out to about 0.6 and some change. So that's between 0 and 1. That's the important piece here. That tells us this is going to be a decay function. So plugging in my same 5 values into this function, let's do, let's see here. For x, we've got -2 to start, so about 2.718, basically e. And then we've got -1 getting plugged in. That's about 1.65. And then if you plug in 0, we've just got basically e to the 0, which is just going to be 1. If you plug in 1, we get, again, that value of 0.61. And then finally, plugging in +2 gives us about 0.37. So we don't need much of a scale to accommodate going from 0 to 2.7. We'll make these pretty small decimal values here. I'm going by 0.4s. So we've got -2, 2.7, which is all the way up here. -1, 1.6 is roughly here. And then we've got 0, 1 is halfway there. 1, 0.6 roughly is there. And then 2, 0.37, that's about 4, so about right there. And then, again, we have that asymptote as you go to the right. So there's our function for that one. So at this point, you might be wondering where we can use this natural base e in real life. I'll show you just one kind of example here involving continuous compounding for finding interest. So you might remember that e, the setup for it, that 1 plus 1 over x to the x, was basically our interest formula with an infinite amount of compounding in it. So this kind of leads into our discussion of how e helps us find an infinitely compounded sum of money. It turns out that the growth factor, if you're going to be compounding continuously, having an infinite number of compounding periods, is just e raised to the interest rate, which is kind of crazy. But we can see why this would be based on what e actually looks like in that weird limit infinite fraction form. So if you plug this into the b value in the general interest formula, p times b to the t, but instead of b, you have e to the r in there. It looks something like this. F of t equals p times e to the r to the t. The t was already in the exponent, and you're just swapping out the b for an e to the r. This is called the PERT formula sometimes. It's really just the continuous compounding formula. And you just have to plug in your values to use this thing to find infinite compounding. So with that said, here's kind of a sample problem for this to give it a test run. Suppose that $1,000 is invested, 7% interest, which is kind of nice, compounded continuously. That's the key word here that we have to use PERT. We just want to know how much money's in the bank after 5 years. Pause the video and give it a try. All right, so let me go to Desmos for this. But first, before I do that, let me actually set things up. So we've got f of t equals p times e to the rt. I like to write this so I know where to plug things in. And then we've got, for this particular problem, a principal of 1,000. E to the r, so the r is going to be 0.07. We still have to use a decimal for that. And then our time period was 5. So just plugging all this into Desmos. Let me just do f. Well, I don't even need to make a function. Let's just do it out. So 1,000 times e, raise the exponent, and then 0.07 parentheses 5, and we get about $1,419.07, just like that. For our final problem here, we'll have a little more involved real-life kind of word problem. Let's say that you and your friend each have accounts earning annual interest compounded continuously. The balance A of your account after 2 years is modeled by this 4,500 e to the 0.04t sort of formula here. And I mean, if you know kind of how the formula is set up, then you might recognize that, you know, this 0.04 here really means we've got 4% interest going on. We don't need to know that for the problem because they've already given us the formula, but it's cool that we can pick that out of there. Now the graph here is showing the balance of your friend's account over time. So we have a function representation for your account and a graphical representation of your friend's account. We want to know which account has a greater principal, that's the starting amount, and which has a greater balance after 10 years. So pause the video and see if you can figure out the principal and 10-year balance for you and your friend, and then we'll bring it back and talk it over. All right, so let's do principal first. So your principal, based on this formula, is going to be this 4,500. That's your p-value right there. Your friend's principal is just going to be the starting amount at year 0 on this graph, which they've spelled out for us. It's exactly 4,000. So based off of that, your principal is clearly more than your friend's. You started with more money in the bank. Now let's see what happens after 10 years. To figure out your 10-year total, you just have to plug 10 into this function. So not too demanding there. So we just have 10 for time. We will need Desmos in order to figure this out. So let me plug into Desmos 4,500e exponent 0.04 times 10. And it looks like your 10-year total is $6,713.21. There we go. Now let's check out your friend's 10-year account. Looking here in the graph at 10 years, it's kind of hard to tell. This is the 7,000 line. This is maybe a fifth of the way up until that next line there. So I'm guessing 7,200-ish. May not be exact, but it's as good as we're going to get from this graph. And it's enough to tell us who has the greater 10-year total. That would definitely be your friend. So that's it for this lesson. Feel free to do some practice problems on that homework set, and after that you can take it easy. Until next time, Mr. Sutton signing off.